So the circuit's been rebuilt. We now have the series capacitor and we have a shunt resistor in the circuit. So the channel 2 of the oscilloscope is across the resistor and channel 1 of the oscilloscope is across the supply, which is feeding the CR circuit. And then once we focus here, then looking at the oscilloscope screen, we can see that I've got 500 millivolts per division on both channel 1 and on channel 2. So both of the voltages are very similar to each other. There won't be much difference there at all. But first of all, we'll go ahead and we'll measure the phase difference. And trying to measure the phase difference while the oscilloscope's set like it is very difficult indeed, because these are quite close together. We are looking for about 7 to 10 degrees based on our previous work. So I'm going to have to stretch this out on the oscilloscope screen so that we can take quite an accurate measurement. So can I just get you to hold that microphone for me? Thank you. And what I'll do, I'll demonstrate how I would do this. I'll use the horizontal control to stretch the waveform out, and I'm going to have to make sure that both channel 1 and channel 2 are lined up over the top of each other. And I've covered this in other videos. There's a detent position there, and it's quite easy when you move the control to ensure that they are lined up. Now it's time now to really think about increasing the gain, and if I think about blowing these waveforms right up on the screen, I'll be able to work with something that gives me much more resolution. Here we go. Moving that along. And go to the cursor mode. Cursor for channel 1. Okay. Line him up at the crossover point, and it's important that I get both the rising or both the falling parts of the waveform. We can see that VC is actually hang on, what have we got here? Channel 2 is VR. I beg your pardon. We can see that VR, which is now represented by channel 2 in the blue, is leading VS. VS is still the yellow, and this is now VR. So VR is, as we saw in the theory, leading the supply voltage. The other cursor, moving that along, I've got my two cursors set, and I get 29.2 microseconds. Now if I run the maths on that, I'm going to end up with 29.2 divided by 1111, because that's all in microseconds, so I don't even need to put them on, it's only a ratio, times the 360 degrees. And we get the calculator, do that on the calculator. 29.2 divided by 1111 times 360 equals 9.46. Ooh, 9.46 degrees. That's very, very close to the 10 degrees that the calculations told me that I should have had before. So don't know what happened in the first part of the lab. The first part of the lab we measured 83. That seemed to be about 3 degrees too much, because based on that this would have only been 7 degrees. We've now got 10. So, and this corresponds pretty accurately against the calculations we did on the board before. Okay, so we're back to it again. We've rewired the circuit to make circuit 1B. Oops, circuit 1B. And in circuit 1B we have what's called a leading circuit, because the output is taken across the resistor and the voltage across the resistor is leading the voltage across the supply. So I've drawn what we saw on the oscilloscope here. Here is VR leading by a fraction in time, in this case the supply voltage in time. Output leads supply, hence it's called a leading circuit. I don't think I said it on the previous circuit, but it's called a lagging circuit because the output is taken across the capacitor and VC is lagging the supply voltage. So in our leading circuit we've still got the 900 Hertz at 1111 microseconds period. We were supposed to start with 4 volts peak to peak, but look, when I sat with one of the students before and I photographed the oscilloscope screen, he had it set for supply voltage of 1370 millivolts RMS, so I left it at that. It's close enough to 1414 millivolts RMS. But it was interesting, the oscilloscope using its automated readout function told us that we had 1370 millivolts RMS across the resistor as well, and that can't be correct. There's going to be a slight difference. They're going to be very close because we only have an angle of phase angle of about 10 degrees, maybe even a fraction less. So I've been able to plot the phasor diagram this time more to scale, and there's what we measured before on the capacitor, 230 millivolts RMS. And now we know that we've got VS at 1370. That's spot on. But VR, it was telling us 1370. Ooh, that's going to not be quite that. Let's check the angle. We run some maths on it. We've got the opposite. We've got the hypotenuse. So we can do 230, which is the capacitor voltage, divided by 1370, which is the supply, using the sine function and using inverse sine, 9.66 degrees on that, and we call it 10 degrees in the previous calculations. And certainly when I sat down with the students we measured 10 degrees. So I'm pretty happy with that. But what about this VR? We need to find the length of that that value, that VR, the voltage across the resistor. And to do that I've been able to use the polar to rectangular function on the calculator. You could do it with Pythagoras as well, but just as easy to learn how to use the calculator and do this. After all, we're always using rectangular to polar to work out the phase angle, so why not use the opposite function this time and put in the resultant, the hypotenuse here, which is 1370 millivolts RMS at an angle of 10 degrees, convert from polar to rectangular to give me that horizontal parameter, 1350 millivolts RMS VR. So I would change that to 1350 and I would change that to 1350 because it's a triangle. You can't have the adjacent side and the hypotenuse being the same length. Just because the calculator automatic display says that they're the same, don't fall for it. It's I suppose it's doing an approximation there, because I adjusted the screen and on the screen it told me I had 1.37 volts. Merrily told me that I had that for both my measurements, and I know that's not correct. So that maths fixes that up. And even here, these are not to scale. Maybe in the horizontal axis they are, but certainly VS is a much different amplitude to VR. Oh well, is it? I suppose we're only out by 20 millivolts difference here in the vertical. We're not out by very much there at all. And certainly the waveforms were very close together, and in the practical lab what we did was to stretch them out horizontally, increase the amplitude on the oscilloscope and use markers across the x-axis so that we could measure that time difference. And we measured that time difference there to get our 10 degrees. that wraps up then circuit 1B for this lab. And when you do your drawings should be pretty well to scale, and you can do a phasor diagram for this circuit, which should look very, very similar to what I've done here. Don't forget scale. If that's 230 millivolts and that's 1350 millivolts, that's got to be about 6 times longer than that, so it's going to be quite a sharp angle in there on the diagram. Okay, hope that clears that up.